The suit that keeps the Fremen alive in the deep desert works by catching your sweat before it can evaporate. That is also exactly how you cook a person. Frank Herbert described the Stillsuit in more detail than any other object in Dune. One paragraph, spoken by a planetary ecologist, laying out the thing layer by layer, and somewhere in the middle of that paragraph, he wrote a sentence that quietly cancels the entire machine. He didn't notice. Neither did anybody else, for about 50 years. So let's do the thing nobody in the Imperium apparently thought to do. Let's put a clock on it. Here's the passage. Litre Kynes, fitting Paul into his first suit. It's basically a micro-sandwich, a high-efficiency filter and heat exchange system. The skin contact layer's porous. Perspiration passes through it, having cooled the body, near normal evaporation process. Read the last part again. Having cooled the body, near normal evaporation. Herbert wants the sweat to evaporate because that's what cools you. And then he wants to catch it. Both, at the same time. Physics will sell you one. Evaporation doesn't cool you by removing water. Water isn't the point. Evaporation cools you by removing energy. It takes about 2.4 megajoules to turn 1 liter of sweat into vapor, and every joule of that comes out of you. That's the whole trick. The water is just the truck. Catch the vapor, and you've caught the truck with the cargo still on it. You have built an extremely sophisticated way to sweat into your own thermos. I'm not the first to notice this. A commenter on Hacker News laid it out cleanly. A student at Embry-Riddle wrote it up as a course project back in 2015. What nobody has done is the arithmetic. You have 4 ways to dump heat: conduction, convection, radiation, evaporation. The first 3 all need the same thing, somewhere colder than you. Now put the desert at 50 degrees Celsius. Your skin sits around 33. The gradient doesn't weaken, it flips. Conduction, convection, and radiation stop being exits and start being entrances. The desert is now heating you. This isn't a Dune fact, it's in the physiology literature, stated flatly. Once ambient temperature passes skin temperature, evaporation becomes the primary route of heat loss. Above about 43 degrees, it's the only one. So when a Stillsuit intercepts your sweat, it isn't disabling one system out of 4. It's disabling the last one. Fine, numbers. You are 70 kilograms of mostly water. Raising your core temperature by 1 degree takes about 209 kilojoules. That figure used to be higher, by the way. The textbook value was an assumption from decades ago that nobody had actually measured. In 2023, a group finally calculated it from real tissue masses, and it came out 17% lower. Which means you heat up faster than the textbook said. Standing still, in shade, doing nothing, your body produces about 85 watts. A dim light bulb. With no evaporation available, that's 1.5 degrees per hour. Core temperature starts at 37. Somewhere past 41, the mortality curve goes near vertical. Call 42 the wall. 85 watts gets you to the wall in about 3 hours and 20 minutes. That's the good news. That's your best case. Standing in shade, not moving, not carrying anything, not doing the single thing a person in a desert is definitionally doing, which is trying to be somewhere else. Step into the sun, and the desert starts donating heat to you. Call it 150 watts net. Under 2 hours. Walk, and you're at 400 watts. 43 minutes! And now the Fremen problem. Fremen don't walk on roads. They walk on loose, dry sand, which is measured, not estimated, measured, at 2.1 to 2.7 times the metabolic cost of firm ground. Le Jeune, Willems, and Hegland, 1998, Journal of Experimental Biology. Sand steals your work. Every step, the ground you just pushed off leaves. And they don't walk normally. Paul teaches Jessica in the second half of the book, and Herbert writes the rhythm out on the page. Step, drag, drag, step, step, wait, drag, step. Deliberately irregular, so a sandworm hears wind instead of dinner. A study last year put a number on what that costs. Roughly 1% more energy for every 1% of extra variability in your step length. Add it up. The most expensive terrain on the planet crossed in the most expensive way available, wearing the one garment that switches off cooling.
The worms don't need to hunt anybody. They just need to be patient.
It gets worse, and this part is Herbert's own text again. Motions of the body, especially breathing and some osmotic action, provide the pumping force. The suit is self-powered. No battery, no reactor, nothing external. It runs on you. Every pump stroke, every filter membrane, every gram of salt pulled out of solution costs energy. That energy comes out of your metabolism. And this next part has no exception clause anywhere in physics. Essentially, all of it ends up as heat. Inside the suit. You are powering a machine whose job is to make you hotter, using a fuel that also makes you hotter. Herbert called it a heat exchange system. That phrase is the giveaway. A heat exchanger doesn't destroy heat, it moves it. And to move heat, you need somewhere to move it to, and that somewhere has to be colder. At noon on Arrakis, there is nowhere colder, unless you look up. There is exactly one cold thing above Arrakis, and it's the coldest thing that exists. Deep space sits at about 2.7 Kelvin, roughly 270 degrees below zero. It is directly overhead all day, whether the sun is out or not. The problem is getting your heat to it. Point a warm object at the sky, and most of its radiation gets absorbed by the atmosphere and thrown straight back down. Most, not all. There's a band of wavelengths, 8 to 13 micrometers, where the atmosphere is nearly transparent, a window, and it lines up almost exactly with the wavelengths that objects at human body temperature naturally glow at. Radiate in that band, and your heat doesn't warm the air. It goes to space. It skips the planet entirely. In 2014, a group at Stanford built a surface that does this. Published in Nature, in direct sunlight, on a rooftop. Their material sat 4.9 degrees below the surrounding air temperature. It was being hit by more than 850 watts per square meter of sunlight, and it got colder than its own surroundings. Net cooling, 40.1 watts per square meter. It's gotten better since. 93 watts per square meter from a glass polymer metamaterial in 2017. 117 from Purdue's barium sulfate paint, the whitest paint ever made. The practical ceiling in the literature is around 150, and they've woven it into cloth. 2016, Stanford again. A nanoporous polyethylene textile that held skin about 2 degrees cooler than cotton. 2021, a paper in Science. A volunteer wearing a vest that was metafabric on one half and cotton on the other sat in direct sun for an hour. The metafabric side came out almost 5 degrees cooler. So Herbert wasn't wrong to want a passive suit that cools you with no power source. He was wrong about the mechanism. And the mechanism that actually works was invented 49 years after he wrote the book. So, does it rescue the Stillsuit? Do the arithmetic. An adult carries about 1.8 square meters of skin at 100 watts per square meter, near the best number anyone has published. That's 180 watts of cooling. Resting metabolism is 85. So yes, standing perfectly still, a radiative Stillsuit works. With margin. Now walk. 400 watts. To radiate that away, across 1.8 square meters, you would need 222 watts per square meter. Higher than any figure ever reported, and about 50% past the ceiling of the entire field. The Fremen could survive Arrakis. They just couldn't cross it. And then there's the dust. Radiative cooling needs a clear view of a cold sky. It is exquisitely sensitive to whatever sits between you and space. Humidity alone is brutal. In one set of measurements, the cooling effect collapsed from 21 degrees below ambient down to 3.5 as humidity climbed. Under thick cloud, the atmosphere goes opaque in the infrared, and the effect stops completely. The window shuts. Arrakis has a permanent dust load and storms that strip paint off metal. Nobody has ever tested a radiative cooling fabric under desert dust. That measurement doesn't exist, and I'm not going to pretend otherwise. But mineral dust over West Africa was measured increasing downward infrared radiation at the ground by about 16 watts per square meter. Same mechanism as humidity. The sky stops being a window and becomes a ceiling. On Arrakis, the one piece of physics that could have saved the suit is the exact physics the weather is built to defeat. Okay, here's the part that isn't funny. Go back to what Kynes actually promises. Not comfort, not survival. Read it. With a Fremen suit in good working order, you won't lose more than a thimbleful of moisture a day. That's the spec.
That is the entire performance claim for the most important piece of technology on the planet. Not, you won't overheat. Not, you'll stay cool. Water retained. The Stillsuit isn't a survival garment that happens to save water.
It's a water recovery garment that happens to contain a person. On a world where water is currency, where the dead get rendered for their moisture, somebody designed a machine to protect the asset.
You're not the asset. You're the container the asset is kept in. And Herbert, who thought harder about this planet than about anything else in the book, wrote that sentence knowing exactly what it said. Every safety system you have ever been handed has a spec sheet. Somebody wrote it. Somebody decided what the thing was actually there to protect. Sometimes that's you. Sometimes you're just where it's kept. Next time, Dune's shields stop anything moving fast and let slow things through. That's the entire reason everyone in this universe fights with knives. Air molecules move at about 500 meters per second. Have a think about that one. Until then, Terrans.